Questions? Okay, let me just tell you the plan for today. I'm going to finish large margin classification, and then I'm going to be talking about non-uniform learnability and structural risk minimization, okay, which is sort of an upgrade on expect ERM. Okay, so large margin classification comes from VC dimension and pack learning. Okay, we want to find an actual algorithm that follows pack learnability. Okay, we want to find a classifier that obeys the pack learnability. Okay, and it's also based on VC dimension. So, as I mentioned, VC dimension was developed or invented by Vapnik, and he, based on VC dimension, he came up with this algorithm called the support vector machine. And before deep learning was popular, the support vector machine was the algorithm that worked well on test data. Okay. Today we're going to focus on binary classification, but this algorithm not only does binary classification, it can do regression and it can also do ranking. Okay, and it's critical that we understand what geometric margin is. Okay, and it has various applications. Text categorization, image classification, handwriting recognition, and ranking. Okay. So maximizing the margin leads to a particular choice of decision boundary, and the location of the boundary is determined by a subset of data points known as the support vector, which are indicated by the purple circles in this picture here. Okay. If you remember, we're trying to separate the red from the blue using a linear classifier. The linear classifier is a line. Above that line is one class. Below that line is another class. Okay, and we can have many different lines separating the two classes. In support vector machine, we're trying to find the widest road between the two classes. So, I could fit various road with the width, and the road should not contain any data point except at the edges. And you can see by the picture here, oops. It's going to take me a while to. You can see that this one, this particular one, is the widest road. Okay, and the width of the road is defined by the margin. Okay, and I went through the definition of margin. Okay. This was a definition of margin. So here is distance of a line, W, here it is, Wx plus B. X is the data, W is the gradient, B is the y-intercept, and all these things are vectors, okay? So that's a linear classifier. That's a hyperplane, I should say. Hyperplane. And in one dimension, it will be a line, okay? And the sign would determine the class, okay? If it lies above, then it's a positive value. If it's below the line, then it's going to be a negative value. So it's going to have a negative value. So this represents right here, this part, this yellow part, as I said, is the distance from that hyperplane to that point xi. That's the distance. This is the sign distance. And then you multiply it by the label. Okay? Now the label, I'm considering binary classification, and the label is going to be +1 and -1. Not 0 and 1, but +1 and -1. Okay? So if the geometric margin is, if the data is in the right side, it's in the right side of the hyperplane, then it's going to have a positive value. If not, then it's going to have a negative value. Okay? Because this, if it's below that line, it's supposed to have the label -1. So this will be a minus, and that will be a minus. So that will be a plus. So if the prediction and the, well, this is not the prediction, but this is the signed distance. So if it's in the right side and it has the right label, then it's going to have a positive value up. Okay? That's gamma. Gamma is the margin for data xi. Okay? And what we would like is to find the minimum value of this margin, geometric margin. So we're finding the distance, we're finding the smallest distance from the decision boundary. So if you go back to this picture, this, if we're looking at this hyperplane, then the points on the edge of the road would have the smallest distance. That's the distance. That's gamma. Other ones will have a bigger margin. Okay. So we're looking at a geometric margin of the data set that is minimum overall training set. Okay? And our objective is to maximize this minimum value. Okay? We want to maximize this minimum value. So we want our decision boundary to be as far away from the data points. Okay? And I should also say that the width of the road, width is equal. So this distance and that distance is the same. Okay? So the closest point of the positive and the minus is the same distance away from the decision boundary. Okay. And I also said that a classifier or a hypothesis that I just mentioned has a VC dimension that is bounded above by this thing on the right-hand side. Okay, and I mentioned gamma is the geometric margin of the data set. R is the radius where all the data sites lie. Okay, and D is the dimension of the data. Okay. And we can see that, we can plug this value into our VC theory. Okay, that's what I've done right here. Here, or here, and we see that this value, so this is the test error or the true risk bounded above by the empirical risk with some confidence interval. The confidence interval is a function of the VC dimension here. Okay. And also the data delta is 1 minus delta is the confidence. Okay. And M is the number of data that's available to us. And you can see that if dr, and then I could substitute for the VC dimension, okay, VC dimension, in terms of R and gamma. And this is what we get. And we see that by maximizing the gamma value, the margin, the confidence interval goes down. Okay? Which means that the test error is bounded above by the training error and small value. Okay. So what this is saying is what we observe with a training set, the error that we observe with the training set is going to be close to the test error. Okay? Okay, everyone understand what I've said so far? Okay. And this comes from our derivation of the VC theory. Okay. And then I talked about how to obtain this large margin classifier or support vector by setting up a constrained optimization problem. Okay. So this was the margin. Okay. This was the margin. And we wanted the margin for all of the data to be at least C. And we wanted to maximize C. Okay. And that would make the geometric margin large. Okay. We rearranged this term so that the denominator goes on to the right, and because you're multiplying two parameters, that unknown parameters, we could set it to equal to 0, 1. And the C, the minimum geometric margin, will be the inverse of the norm of the theta. Okay. So maximizing the inverse is minimizing the norm, is equivalent to minimizing the norm. And instead of minimizing the norm, we minimize the square. Okay? So this was the constraint optimization problem. Okay? And then I reformulated this into min-max of the Lagrangian. Okay? Lagrangian here. And I went through why this would ensure that on the top. Okay. And I also mentioned that there is a Lagrange multiplier. The number of Lagrange multiplier is equal to the number of training data set. So going back to this figure here, all the sample data would have its own Lagrange multiplier. And all except for the support vectors are those data that are on the edge of this road, the data that define the hyperplane. All of the Lagrange multiplier for all of the data, except for the support vectors, are equal to 0. Okay. And I also mentioned that the solution, the final hyperplane, so this is our prediction. I predict, let's say it's a function of fx, is going to be in this form. It's going to have the data, label. This is training. This is the ith training. Okay. These are ith training. Data, and that's the label, and that's the corresponding Lagrange multiplier. And that will be the input. Okay. And I said that except for the support vectors, all the Lagrange multipliers will be 0. Okay, so I need to sum this up for all training data, but because Lagrange multipliers are non-zero for support vectors and 0 for others, you're doing sum over all the support vectors. Okay, and then you would have to look at the sign of this to determine or to predict the sign of this label. Okay. And you could derive that. Okay. So this comes from the training data. You need to determine what the Lagrange multipliers are. Okay, and you need to pick out which one is the support vectors. Then I talked about constrained convex optimization, which leads to a unique solution. Okay, and convex optimization is defined as minimizing a convex function over a convex set. Okay? Only then you have a unique solution. Otherwise, you don't have a unique solution. Okay? So I defined convex function. Okay, there are 2 ways to define that. Then I also defined what a convex set was. Okay. And here are a couple of convex functions. Okay. You're probably familiar with the square laws. Okay. Today I'm going to be talking about the hinge loss. Okay. Hinge loss is this blue thing here. Hinge loss is this blue thing right here. So it's positive value, and after 1, it's 0. Okay, that's the hinge loss. And mathematically, you can write it like that. And this axis is z, and this z for this case is yi f xi. So what is this? This is the label of the ground truth. Oh, it's ground truth label, I should say. Ground truth label. And that is the prediction. Predicted label. So when the predicted label, the ground truth label are in agreement, this value would be a positive value. And if it's greater than 1, then this whole thing takes value 0. But if they are in disagreement, this one is positive and this one is negative, then this value will be a negative value. This would be a negative value. And you got another negative value. So that's positive. So the maximum will be this value right here. And as this value goes more negative, it's going to be a line like that. Okay? That's called the hinge loss. And we're going to be using this hinge loss for defining soft SVM. Okay? I also introduced a method for obtaining a solution to the constraint optimization problem. Okay? An algorithm that will work for all cases. That was a gradient descent. Okay, so you're given a general problem. And gradient descent, by the way, is an iterative algorithm. You start with some initial point, and then you iteratively update your point or solution. Okay? So what you do is you're at some point theta t, you go in the opposite direction of the gradient at some scale, eta, to obtain theta hat, and then you project that theta hat to the space, the constraint space. Okay, you project it to obtain your update. Okay? And you keep on doing this. This algorithm, gradient descent algorithm, and if you do it for each data, that's called stochastic gradient descent. SGD, stochastic gradient descent. It works for all constraint optimization problem, but I said that it is slow. It converges to the solution at a rate of 1 over root t. T is the iteration, okay? And there are various algorithms that converge faster. Okay, here is the derivation, and I'm not going to go through it. Okay. Now I want to introduce soft SVM. Okay. What I've explained so far is hard SVM, or just SVM. What is soft SVM? So hard SVM is here, you're trying to classify the green points from the blue points. You got a decision, boundary, and you got this road. You got this road. And you want to make that road as wide as possible. And you can see the support vectors are on the edge of the road. By the way, I want to define functional margin. Let me just rewrite this thing. It's geometric margin times the norm of theta. Okay? Who can tell me what the functional margin of this thing is? Of the support vectors. What is the value of the functional margin in our derivation for hard SVM? Look through the notes. What is the functional margin? Anybody want to give a guess? If you remember, so this was the geometric margin, and I wanted geometric margin to be at least C, and I was maximizing C. I had this denominator go to the right and said that was going to equal to 1 without loss of generality. Without loss of generality. So, what is the functional margin of the support vectors? The functional margin of the support vectors are 1. Okay, it's 1. And my hard SVM had no data within this region right here. data was not allowed. Okay, and that's how we obtained our solution. In soft SVM, we're going to relax that condition. And we're going to allow data to be within this region. Okay? And I'm going to introduce a variable called the slack variable. Oops. Slack variable is the distance of a particular point, so the ith data point, being away from the line where the functional margin is 1. So it's violating by psi I, this data. Okay? Data on the correct side will have psi equal to 0. So all the psi i's for these will be 0. Only if you're violating, if you're in that region, you get a positive psi I. Oh. And so we can see that it's sort of like a hinge loss. Oh. Anything, so when psi is psi, okay, it's some positive value, okay, and after that, then it's 0. Right here, it's all psi i's are all 0. Okay. And on the other side, it's the same thing. This one is violating by this distance. Okay. Okay. I think I need to update my slide because I'm sort of cut off. And you can see that. Oh, let me just. And what I'm going to do in soft SVM, all the training data is going to satisfy this equation. Okay. Before we had psi I all 0. But I'm going to allow for some psi I. So in the hard SVM, I had theta transpose x plus theta naught being greater than 1. They're all equal to 1 or greater than 1, right? At the functional margin of all the training data, because none of the data was within that region, that forbidden region. But now I'm going to allow, I'm defining psi I, I'm going to allow some of the data. In fact, I'm going to allow all of the data to be within that region. Okay? And I'm going to say psi I is always non-negative. Okay? It's just the distance. And my objective is not just to minimize the, not maximize the margin. Maximizing the margin means minimizing the norm of theta, or theta squared. I'm also going to try to minimize the sum value of psi i's, or sum or the average value. So I'm going to try to minimize the accumulated violation. I'm going to try to minimize the accumulated violation. If going into that region is, if you consider that as a violation, I want to minimize that. Okay. So this is soft SVM. This is soft SVM. So I want to maximize the minimum geometric margin as well as minimize the violation, the average violation. Okay? And it turns out that this can be formulated into this function with the hinge loss. So the hinge loss is right here. Okay. So minimizing this sort of maximizes the margin, and this and that combined gives me some average value of the hinge loss of each of the training data. Okay. Okay. Because psi I, the psi I is defined as when the functional margin of data I is greater or equal to 1, psi I is equal to 0. Otherwise, it's this value right here. Right? And you can use stochastic gradient descent to minimize this. Okay? And also, I should also say, gradient descent required that you take the derivative of the loss function. Now the loss function, in this case, is a hinge loss, and the hinge loss is not a continuous function. Okay? It's not continuous at 1. Okay, coming from the left, coming from the right, your value is different. Okay? So how do you define this gradient? The loss function has to be a continuous function in order for you to take the gradient. And instead of taking the gradient, you could take the subgradient. Okay? Subgradient is defined as a line where all the functions lie above that line. So let's look at this case, the blue function, which is not continuous. It's not continuous right here, right? And the subgradient will be all these red lines. So it's not unique. You can choose any one of them to be the subgradient. all the function value lie above this line. Let's look at a continuous case, this blue one. What is the subgradient right here? Will be the gradient, right? If the function is continuous, the subgradient is unique. If the function is not continuous and it's at some point, then the subgradient is not unique. Okay, there are many possibilities, and you can just choose one. And using gradient descent, instead of using the gradient, you could replace the gradient with the subgradient, and it works perfectly well. And obviously, you're going to choose a subgradient that doesn't require a lot of computation, because you have many choices to choose from. Okay, so the subgradient will be denoted as V. Okay, and so it's exactly, the full algorithm, stochastic gradient descent, would look like this. You choose any data, okay, and you set theta to be some random value. Okay, I uniformly means just pick any data, and then you find out, you take the subgradient, and then you do a sort of an update by going in the negative direction of the subgradient. Okay, and then you project it to the constraint that you have. Okay, the details are in this slide. Okay, you can go through it, and we're going to ask you to implement this in the homework with a different data set. And here is an example of binary classification. You have red points, blue points, and you can see that the red and the blue are non-linearly separable. Non-linearly separable. Meaning that there is no hyperplane that will separate the blue from the red. You can see that they are sort of mixed in the boundary. So you will not be able to find a solution for hard SVM. You would have to use soft SVM, which would allow for some violation. Okay, so we're going to use soft SVM. And here is the iteration. After 100 iteration, here is our solution, the green one. Then after 200, it's there. After 300, 400, and 500 iteration of going through this algorithm right here. Okay. And here are some details regarding this. Okay. SVM can be used for ranking. Okay. And how does it rank? You're given lots of data, and you take pairs of this data, 2 pairs, and let's say you have a linear scoring function. The scoring function will rank it so that the one that's ranked above would lie above the line, and the one that's ranked below will lie below the line. Okay. And so you have a whole bunch of training data. You pick these two, and then you know the rank because it's training data. You're given that, and you train it so that, what do I mean by training? Find a W, okay, such that you give me any 2 points, and it will tell you the one that is ranked higher. It will give you the order, okay? And based on picking these two, you can find the order between these 2 pairs, and then you can find also the rank of the whole set. Okay? So that's how you would do ranking with support vector machine. And you could also do regression. Okay. Regression is that can be done by using a linear function for predicting the label of the input X, and then looking at the difference between the predicted value, this is the predicted value, ground truth, look at the error difference, and you compare it with epsilon. And you want this value, this loss function, to be small. So you want the error in the prediction to be less than epsilon. Okay. You want it to be small. Okay, and so you set up constraint optimization that looks like this to allow you to do this. Okay, that's support vector regression. And that ends my talk on large margin classification. Okay. So why are we trying to maximize the minimum geometric margin of the training data? Because that will reduce the confidence interval so that the training error and the test error are close. Okay? And that follows from the VC theory. Okay? We proved that the test error is bounded above by the training error plus the square root of this term, which was a function of the growth function. And the growth function can be upper bounded by the VC dimension also. Okay. And we can find the VC dimension of a linear classifier, and we're trying to maximize the margin. So the classifier is trying to use a hyperplane and maximize the geometric margin. Okay, we can find the VC dimension of that. Okay, so that, any questions? No questions? Okay, good. Now I'm going to be talking about non-uniform learnability and structural risk minimization, SRM. So just to recap, I hope people remember uniform convergence. In order to understand uniform convergence for the non-realizable case, okay, we first have to know what epsilon representative samples are. Those are the samples where the training error and the test error is very close. Okay, it's less than epsilon. Okay. So this is a property of the training data. Okay. Training data is epsilon representative with respect to all this. Now, this happens if the hypothesis class has the uniform convergence property. And what is uniform convergence property? It means that there is a sample complexity. Okay. Sample complexity is a function that takes epsilon and delta. Okay. If you remember, epsilon is generally, the accuracy, and 1 minus delta is the confidence that we have about our statement or relationship between the training and test data, test and training data. So you take epsilon and delta, and it gives you some natural number. So sample complexity is the size, the minimum size, such that the pack or agnostic pack statement holds. And if we have sample size greater than the sample complexity, then probability of 1 minus delta, S is epsilon representative. Putting all this together, we get this agnostic pack statement. Hypothesis class has uniform convergence property, then this is true. The test error is bounded above by the minimum test error that you will get by going through all the hypotheses in the hypothesis class. This is the minimum test error. Maybe you're not able to find this. It's bounded above by the minimum value plus epsilon. And this does not happen all the time. It happens with probability greater than 1 minus delta. And in order for this to happen, you need to have samples greater than the sample complexity, which is a function of epsilon and delta. Okay? This is what we covered. And we also related this to VC dimension. Okay? We learned that if the VC dimension is infinite, then this is not going to hold. Only for finite VC dimension, it's going to be agnostic pack learnable. Okay? Today, I'm going to give you a hypothesis class that has infinite VC dimension, but it's going to be pack learnable, or it's going to. Okay. So let me just start out by saying that. So in this statement, for all the hypotheses in the hypothesis class, for any one of them, we needed this many samples. The samples had to be greater than the sample complexity, one value, right? I'm going to relax these conditions and say, I'm going to find some sample complexity that is hypothesis dependent. So for instance, if I had a linear classifier and I had another one that's quadratic or higher order polynomial, it would be wrong to, well, it wouldn't be wrong, but it would be sort of unfair because the linear hypothesis would require less data than the quadratic or higher order polynomials to give you good performance. This is one. So if my hypothesis class contained the various nth order polynomial, the nth could be 1, 2, 3, 4, 5, 6, 7. Here, this statement is saying one training size, and then I'm going to compare linear, quadratic, high order polynomial. Maybe that might be unfair. So what I'm going to do is relax this thing and consider sample complexity, which is a function of the hypotheses. So we saw the sample complexity is a function of epsilon and delta. Now the sample complexity is epsilon, delta, and hypotheses. Okay? So beyond uniform convergence and finite VC dimension. Okay? Many of our classifiers may not be finite VC dimension. If it's not finite VC dimension, then it's not pack learnable and we would not consider it if we follow this. It's not because it's not agnostic pack learnable. And uniform convergence is also a very tight constraint. So we're going to relax this and say, can we allow the required sample size to depend on specific hypotheses? Okay, and then I have this definition that the book has. So let me just, without going into a lot more detail, rather than going from uniform convergence, where there's going to be a single, the word uniform, I should just say, the word uniform comes from the fact that we have a single sample size such that the empirical risk of all hypotheses in the class So this is the sample loss is epsilon away from the true risk with high probability. That's uniform. That's why you use the word uniform. One sample for all hypotheses. One. We're going to do pointwise convergence. So each hypothesis will have its own rate, your own sample complexity. And we're going to allow for that. So this is sort of given the distribution of some data, your hypotheses, and you take M samples, uniform learnability. There is an M, there is a sample size which is greater than the sample complexity, which is a function of epsilon and delta only, and then you get agnostic pack. Non-uniform learnability is you include this H, the hypotheses. For each hypothesis, you have some hypothesis class, hypothesis sample complexity, and if you have more samples than that, then this is true. Okay, so A is your learning. So here is your test error plus epsilon is bounded above, this is bounding your test error on the prediction that you found using some algorithm A on sample data, and that probability is greater than 1 minus delta. Okay. And if you can do this, uniform learnability, if you can, for all the hypotheses, you can do that, then it's certainly non-uniform learnability. So, okay. Now, we're going to consider the union of, so this structural risk minimization, we're going to look at particular hypothesis class, which is a union of hypothesis class that satisfies the uniform convergence property. Okay. So let me give you an example. Polynomial again. How is this? N represents the order of the polynomial. What is the VC dimension of a linear classifier? N equals 1. What's the VC dimension of that? You probably have that in the homework as well. 2, right? 2 points, linear, obviously, right? 2 points, plus or minus, you can, not 3. What about second order polynomial? Let me just tell you, it's 3, okay? And if you have an nth order polynomial, then the VC dimension is n plus 1, okay? And I have it here. So obviously, if you have an nth order polynomial, then you can, for nth order, n data, n plus 1 data, you have an nth order polynomial that can go through n plus 1 data, right? Exactly, because you got n plus 1 parameters for an nth order polynomial. So the VC dimension of an nth order polynomial is at least n plus 1, because it can go through n plus 1 data. You can label it any way you want. N plus 2, can it label anything for n plus 2 data? And it turns out you cannot. And the one example is you got n plus 2 data, and there are, let's say the labels are -1, 1, and alternating. So you got n plus 2 data, and the labels are alternating. Okay? Then the polynomial has to go up and down like this. And it has to have at least n plus 2 roots, because it has to go through the zero crossing. It has to go through this 0 in order to do plus and -1, or minus to plus. Nth order polynomial, nth order polynomial does not have n plus 1 roots. Okay? So it can shatter n plus 1. Okay, so VC dimension of a polynomial, nth order polynomial is n plus 1. Okay? Anyways, I'm running out of time. So I'm going to give you a particular kind of a hypothesis class that has infinite VC dimension. But it's constructed from hypothesis class that have finite VC dimension. So the hypothesis class are nested this way. What is an example of a nested hypothesis class? It's the nth order polynomial. So H1 will be first order polynomial, H2 will be second order polynomial, and so forth. Okay? So they are nested. And each of them have a finite hypothesis, a finite VC dimension of n plus 1. But if I take the union of infinite number of them, then the VC dimension is infinite. Okay? And next lecture, I'm going to show you that this hypothesis class, which is constructed from hypothesis class with finite VC dimension, nested, will satisfy that condition, like the agnostic pack. Okay? And it would also be a generalization of ERM, which only tries to minimize the training error. Okay, I stop here. Any questions? Okay, if there's no questions, I'll see you next week.